enclosed by this region?
Solve in terms of x.
Solve in terms of x?
Find the intersection. So
Well, before that, what should I draw?
the graph.
Sketch it, right? Does it help at this point to sketch these things? Yeah, it does. And yeah, you can do that by isolating y. Y is equal to 1 minus x, mainly because what we think of as graphing functions, we tend to like isolating y, correct?
Yeah, it's just that with the y squared.
Yeah, you just have to do 2, right? I mean, this is, you know that y squared is equal to 1 half x. So y is going to be equal to plus or minus the square root of x over 2. Right? Are we okay with that so far? So it's a sideways parabola.
Mhm.
So what does this thing look like? Y is equal to 1 minus x. Well, that's terrible straight lines. Y equals 1 minus x. Just rough sketching. We're not interested in something too exact here. Y equals 1 minus x. Where does that cross the y-axis? 1. And then when x is 1, where is it? Yeah, there it is. So we have our first function right here. Y equals 1 minus x. The other function, does that go through the origin? Sure does. And it's a sideways parabola. What does it look like? It starts here. It's going to go like this, and it's going to go. Am I super concerned about how accurate my curvature is? No. Is that good enough?
Yeah.
Do you have an idea of what the area enclosed by the graph is?
Yeah.
Absolutely. So you could shade it a little bit. Here it is, right there, if you really wanted to. Yay, there it is. Happy stuff. Let's write the integral in terms of x. You would integrate from 0 to 1 half. What's the upper function? I'm talking about this one. What's that one? Yeah, it's going to be the square root of x over 2, right? But then what do you subtract from it? The negative square root of x minus 2, the lower one. This yellow correlates right there, and then you have the blue one all the way to there. Correct?
Yeah.
Dx. And then what do you add to it? The integral from 1 half to what? To 2. Now what's the upper function? It's 1 minus x, thank you, yep. 1 minus x, and what are you subtracting from it? Negative square root of this, right? Now, can you do this if you wanted to?
Yeah.
Sure, you could if you wanted to. Is there a better way to do it?
Yes.
Absolutely. So if you, y, so what's our upper function? Well, first of all, let's set the limits of integration. What's the lower limit of integration for this one? For y value, what's the lower y value? Negative 1, and it's going all the way to 1 half. In this case, what's the upper function? What color is it? The blue one, right? And that blue one is x plus y is equal to 1, right? And remember, this is all in terms of what? It's now dy, so everything needs to be written in terms of y. So this is going to be x is equal to 1 minus y. It has to be in terms of y. It's fine. And then what are you subtracting?
You're subtracting the
You know that x is equal to 2y squared. 2y squared. Is that a little easier to deal with? Yeah, that's a lot easier I think that's a lot easier to deal with. Absolutely. Absolutely. Should you theoretically, if you did both, get the same answer?
Yes.
Absolutely. Yeah. Absolutely. What Andrew did, which is really important here, he was plotting the intersection of this line. That's why he got y equals -1 or y equals a half. So he really wanted that half value because this, right, is 1 half. And he knows it's going to be a reflection because it's symmetric. It's going to be -1 half. It just you have to understand what's going on. We're going to take a nice shape that you've seen before. We're going to take a circle. We're going to place it on a set of axes right here. The center is going to be right the center of the circle. We're going to center it right about the origin. So let's say, for example, I were to take just the upper half of this right here. I would take the upper half and spin it about the x-axis. So if I took that half and I spun it about the x-axis, what would I be tracing out? A sphere. I would be chasing out a sphere. So let's say we want a radius of r here. Let's say we wanted a radius of r. Let's stay in 2 dimensions for a second, just to write this out. If we were to break this up into 2-dimensional pieces, we would be looking at these rectangles right here. Here are some rectangles we would have. Happy rectangles. Nice. What are we going to do with these rectangles to get a rotational solid? We're going to rotate them. So let me draw one of them for you. So if I have one of these rectangles, say it's right here, and I were to rotate this, I would get its reflection down here, but then it would also trace out everybody see the washer that I'm oh so poorly drawing?
Yeah,
Do you kind of see it?
I see it.
Goes right there. So the front face of that washer is right here. There's the front face of the washer. I know, I didn't use multiple colors, and as a first attempt, this is pretty bad. But do you understand what I'm trying to do right there? Yeah, I mean, I'll get better. I'm warming up here. I mean, usually I don't shade in the front here, and I shouldn't connect it right there. That's a little better. So like this right here is the edge. Is that a little better?
That looks more like-
Yeah, that's good. It's a little easier to see. Generally speaking, when you're drawing things in 3 dimensions, the fewer lines you draw, the better. Okay, so if we wanted to find the area, the volume of that one slice, if we wanted to find the volume of that one slice, you would need the height. This is just a really, really short what? Just a really, really short cylinder. The height in this case is our dx. We good with that? The height. So, I mean, if we're looking at it sideways, this is the height of this really short cylinder is what I'm saying.
Right.
Now, the area of this front face, generally speaking, the way it's going to be notarized, the area of this face right here, does everybody see that face, the top of the quarter right there, is going to be notarized as A of X. The surface area of that surface is going to be notarized as A of X. Okay? If we wanted to find the, what shape is this surface area?
Circle.
It's a circle. So how do you find the area of a circle?
Pi squared.
Pi times the radius squared,
Which is the function.
which is the function, exactly. In this case, it's going to be the function that the upper bound is following, right? So in this case, am I allowed to factor out the pi? Yeah, it's a constant. So we have pi on the outside here. And then we have the square root of what?
R squared minus X squared.
R squared minus X squared.
Squared.
Squared, exactly, correct.
Yeah.
Dx. Ah, is that convenient that it's squared?
Yeah.
It's mighty convenient. So we have pi negative r to r of capital R squared minus
X squared.
dx. Essentially, how many integrals do you see? 2. We can keep it as 1, though. So it's pi times, what is it going to be? R squared x minus 1/3
X cubed.
times what? Well, from what to what?
Evaluated from
Negative r to r. So we have pi times r cubed minus 1/3 r cubed minus negative r cubed. And then you have to be really careful, it's going to be positive, right? Plus, like this. So what do you end up with? Pi times 2/3 r cubed plus what? 2/3 r cubed. So what do you end up with? 4/3. Yeah, that's right.
Pi r cubed.
That's correct, right? Did I get that right?
I'm thinking there's something missing here.
Did I? Is it correct? No, hold on. I know what I'm coming out with. I just want to make sure I did the math right.
That's 2r
Plus, that's 2r cubed. Plus, minus r cubed.
Oh, I'm sorry. You know what that was called? Wishful algebra.
Yes. It worked.
It worked. I was like, I know what I'm at. I know I'm okay. So I'm just, I see that all the time where I give you those questions where I'm like, prove that the answer to this question is 7, right? And the kids, the work translates to this sound. 7. You know? Do you understand what I did there?
Yes.
I'm cruising along. So what is it? It should be 2r cubed
minus 2/3 r cubed.
minus 2/3
R cubed.
r cubed. Now, is that okay still?
Yes.
Yeah. Okay. That equals 4/3 pi r cubed.
What you previously wrote also worked. You just worked
Did it in a different order.
Yeah.
Yeah, it worked. I know. This is better though.
You wouldn't-
I like this. This is okay. Just leave it like this, okay? Is that the correct volume?
Yeah.
4/3 pi r cubed? It is. Can you tell me one thing though? Here's what's interesting. We just did a bunch of calculus, but we used one formula that we did not prove. There's a formula we used right there. What?
Pi r squared.
Yeah, the area of a circle is pi r squared. Did we prove that yet?
No.
No, we didn't. Is it actually not trivial to prove that? Yeah, it's not trivial. It takes a little bit of work. But as long as you're okay with assuming that the area of a
Well,
circle is
actually,
pi r squared, it's
We
not
can do it
trivial.
this way.
Ah, can we?
We can
Really?
do
Let's try it. Let's try it. No?
What I was trying to say is like You can take,
Hold on, ready? I think you're saying this. You have this, right? And you just double the area of the arc, right?
Yeah.
Let's try it and see what happens. It's x squared plus y squared is equal to what?
constant R.
Some r squared, right? So again, y is equal to the square root of r squared minus x squared.
You forgot the
Squared, yeah, it blinks, yeah. So are we okay so far?
yes.
So we're integrating from negative r to r of what?
Square root of
The square root of
R squared
minus x squared dx. Good luck with that.
Two times.
Times 2, yes. It is times 2. Good luck.
Well, we know that's times some constant.
Good luck.
Yeah.
Think about it. What is this? What should this come out to be? Pi r squared. There's no pi in there right now. Okay, when you're generating universal constants, something interesting is going to happen, right?
Yeah.
Can you use u substitution on that?
No.
No, there's no x on the outside. There's no easy way to do this.
I know the way.
I know there is a way to do it. We're not going to do it now. Okay, go ahead
Google.
with one. So let's say I asked you this. We're going to rotate y equals the square root of x around the x-axis. And it's going to be bounded from, let's say, x equals 1 to x equals 4. Find me the volume of that shape. Maybe I'm totally wrong. I could be.
Should be a hole.
Okay, well, I'm seeing this. Y equals the square root of x is the same function we just dealt with, correct?
From
So
Y
you have-
1 to 3.
I understand, but you're doing from, this is the square root of x, correct?
Mhm.
So you're taking it and you're rotating it around the y-axis, so you're going to end up with another one on this side, correct?
Mhm.
And you're going from y equals 1, let's say right here, all the way to 3, let's say right there. So what shape? There's no hole in the middle of that. It's just cut off at the bottom and cut off at the top. There's no hole through this thing.
Oh.
There's no hole through it, right? So here's the top of it,
Oh.
right? Are we good so far? So there's your shape right there. So that if you wanted to look at these washers, here they are, right here. Do you see it now? This fun thing, and where are you plugging it in? Right there. So you have pi integral from 1 to 3 of y to the dy. That's correct. Yeah, absolutely.